Alright, so it looks like what really matters is the phase associated with the amplitude of probability for each path. So if the norm doesn't matter, we can choose it to be 1. In this case, this is called a phasor. To understand what can affect the phase, let's go back to our analogy with the waves. So the phase is what determines the position of the wave, so where it is its maximum and where is its minimum. So we all know when we look at a wave at the surface of water, for instance, that the waves are moving in time. So it makes sense to consider that the phase will also be proportional to time. We also need to take into account how fast the wave moves. So we should introduce the velocity of the wave. But we know from classical mechanics that what matters is energy. And the part of the energy which is a function of the velocity is the kinetic energy. So it makes sense to introduce the kinetic energy in the expression of the phase. So the larger the kinetic energy, the faster the phase is expected to move. Now what about the potential energy? Consider an increasing potential energy. In classical mechanics, that slows down the particle. So we would expect that the phase will also slow down if the potential energy increases. So we need to have a minus sign in front of the potential energy. The kinetic and potential energies are defined at a given time. But what we really want is the change of phase over an entire path, and that should be integrated over time. Of course, you recognize action as the time integral of the Lagrangian itself, expressed as the difference between kinetic energy and potential energy. So let's consider that the phase is indeed proportional to the action, and we will write the coefficient of proportionality as 1 over h bar. Of course, that's a guess. It's only a guess what we are doing here, but it's a quite educated guess, and it turns out that this is the right expression we need in order to reproduce experiments